Hi everyone, my name is Meng Yue. I am electrical engineer at Brookhaven National Lab. In today's presentation, I'm going to discuss the exact quantification of system reliability indexes in probabilistic continuous analysis, or we call it PCA. Some background information. In current PCA tools, in general, we use a rare event approximation. We use it to approximate the system problem probabilities. Then we calculate frequency and duration times. The issue with this rare event approximation is it's over-conservative, and in general it leads to large errors, or sometimes the probability calculated can be larger than 1.0. So therefore we need better quantification methods. That's why we introduce these two methods. The first one is called minimum car-set upper bound, MCUB. It's a better approximation. The second one is so-called binary decision diagram, which is used for the exact quantification of the system probabilistic indices. MCUB method is also a first-order approximation method. The benefit is it doesn't lead to probability larger than 1.0. So it also works well for coherent system. That means in Boolean representation, we don't have a NOT gate, only AND or this kind of logic expression. BDD is based on Shannon decomposition. It's a compact encoding of the truth table of Boolean formula. So it is able to calculate the exact system probabilities. So in PCA, the input includes a list of continuances and also the outage statistics. Then we can calculate the system probability, then calculate frequency and finally duration time. We have implemented both methods in a standalone Python script. To test the method, we made up 4 continuous lists. So in each of the continuous lists, we have different single outage numbers. Then we use single outage to create a double and triple continuances with different numbers, as you can see in the second column here. So what we do here is we use BDD to quantify the exact system problem probability, then frequency, then duration times. They are all exact. Then we compare the probabilities and frequency duration calculated using rare event approximation and MCUB method. So overall, BDD provides the basis for comparison. And for the probability, rare event usually gives fairly large errors. As you can see here, in the last continuous list, the probability is larger than 1.38. That's not making sense. And MCUB, the probability is not that too far from BDD, as you can see from there. However, the frequencies and duration times, they are significantly different from the true value. So this is the conclusion we can get. BDD gives the exact value. MCUB gives pretty good probability approximation, but not frequency and duration. And rare event approximation gives the worst results. So conclusions, we investigated more accurate quantification methods here. The major benefit of using this kind of methods include, first, it reduces the conservative in decision making. Second, it increased the confidence of practitioners in the PCA results. If you look at the probability larger than 1.0, you don't have too much confidence in the results. And third one is if you want to develop probabilistic planning criteria, it's better to use the exact value. So BDD provides the basis for developing this kind of criteria. Next steps include a case study based on utility scale system. And also, we are looking at the outage modes related to renewable generation. It has a multiple outage mode. So BDD is not going to work. Instead, we are working on this so-called multi-value decision diagram to quantify the exact probability, frequency, and duration time. Thank you for the interest in this paper.